Okay, so this is part 2 of the comparing linear, exponential, and quadratic function lesson. So hopefully at this point you've gone ahead and made your own attempt at example 4, the application problem. And so now I'm going to work through it for you, and you can confirm that your attempt is hopefully correct. Okay, so what we have is our real-life application modeling problem. We have a table of values that for which the x values represent the cyclist's speed in miles per hour, and the y value represents their breathing rate, the number of liters of air per minute. Okay, and so first and foremost what we need to do is see if from the table we are able to ascertain what pattern we have, and this is going to allow us to determine what kind of function, and this we're going to confirm by graphing the function, or in fact what we'll do is we'll graph the function first as per the instruction. This should give us an indication of what kind of a function it is, and then what we'll do is use the table of values to do the calculation. And so what we'll do is begin by plotting the points. You'll notice in the graph what's typical is for kind of this zigzag at the beginning here to indicate that the values to the left of 16 for speed and below 46 approximately for liters per minute for the breathing rate are not relevant. And so just to get a proper perspective, we're only showing a portion of the graph so that we can isolate that portion and get an accurate view of what the graph looks like. So we're just going to go ahead and plot each of these. Remember, these are ordered pairs, x equals 20, y equals 51.4. So we'll do our best to get a reasonably accurate graph. So we have 20 and around about 51. We have 21, 57.1. And so we have the point 22, 63.3, 23, 70.3. 24 is the value of 78, and 25 gives us the value of 86.6. And so if we take these and do our best to try and join them, hopefully what you'll see is that it's a somewhat linear shape, but doesn't really adhere to the linear function, and that should be reasonably obvious because each jump in the x value is constant. We're increasing by 1, but the number of jumps in the block definitely, in other words in the breathing rate, is not constant, and so our slope is not constant, and so that should immediately eliminate the possibility of a linear function. Of course, this could be exponential were the graph to take the following shape, or indeed could potentially be one of the branches of a quadratic function. And so what we're going to need to do in this case to be sure is to go and to look at our table of values. Okay, and so what we could do is start off by determining if we in fact have a common ratio. So what we're going to do is pick 57.1, divide by the previous term, and that will give us the ratio. And so we'll go over here to the calculator, 57.1, and we are dividing by 51.4, and what we get is a value of 1.11. So we're going to round off 1.11, and then I'm going to repeat this just to check if what we have is a ratio which is constant. And if we do, then we've established that it's exponential, and if we don't, then of course we'll go ahead and test for it being a quadratic function. So in this case I'm going to take back to the calculator, and we're going to take 63.3, and we're going to divide that by 57.1. And what we get is a value which once again is extremely close, 1.108, which with rounding would give us the value of 1.11. And so again, since this is a real-life example, mathematical model, we can't expect too much precision. There's going to be a margin of error that is reasonably close enough for us to conclude at this point that what we're looking at is in fact an exponential function, and so what we're after is a function in the form y equals a times b to the power of x. So in the previous note, the instruction was to use the value that x is equal to 0 in order to find the a value. In this case, we cannot do that because we don't have a table of values with 0 in it, and we do not have an equation. And so what we can do, though, is use the same approach as we used with a quadratic. Select any point, substitute it in, find the corresponding values. So what we can ascertain immediately is that 1.11 is our common ratio, and therefore that is our base. And so we can begin by writing part of our equation, y is equal to a times 1.11 to the power of x, and what remains to be done is to solve for a. We can select any one of the points in the table of values in order to be able to do this, and so again, for no particular reason, I'll select the first one, and what I'm going to do is go and substitute that in. The y value is 51.4 equals a multiplied by 1.11 to the power of 20, and we can use that to solve for a. Okay, and so what I'll do is 51.4 divided by, I'm going to open a set of parentheses, 1.11, and that's going to be raised to the power of 20, the corresponding x value. Okay, and what we have there is 6.375, and so I will round that to 6.38 for the a value, and we can now write the equation 6.38 multiplied by 1.11 to the power of x is the exponential function that models speed of a cyclist relative to breathing rate, or breathing rate relative to speed. Okay, so hopefully you are able to do that, or do at least a significant portion of it on your own. What you need to do now is make sure that you have completed examples copied down so that you can refer to them later for when you are studying. And what you need to do is turn your attention now to the assignment detailed on your note. Start off by focusing on the level 2 as usual. Work on that assignment, and in the event that you finish that during regular class time, then you need to begin working on the chapter test in preparation for our test on quadratic functions, which is coming up in a couple of classes time. So we will have a review class next time, but if you start working on the chapter test assignment, this will help you to get a little bit ahead, and answers to the test questions are posted on Blackboard.